All right. So here we will talk about Chapter 4. The normal distribution here, okay? And the normal distribution, it's basically describes a random variable, okay? So some random variables follow the normal distribution. Okay. The normal distribution pops up a lot in nature, okay? So that, you know, we see this a lot, quite frequently, you know, in nature and populations. Okay, and I guess that's why it got the name normal, because it gives us an idea of what is normal, and basically, okay, you know, it looks. Let me. I think I'm going to cheat in a moment and just use the pre-drawn normal distribution, but it looks something like this. Okay, it looks kind of like a hill, and so this is we would describe this as unimodal and symmetric. And basically, in the center we would have our mean of the distribution. Okay, and the you know, the height of the graph represents how frequently those values appear, right? So kind of the frequency. And so what we see is that values close to the mean appear most frequently. Values that are close to the mean appear most frequently, and values far from the mean, okay, so, you know, out here, so this would be frequent. Maybe I should use a different color there. Okay, and then over here would be rare. Okay, and then so values far from the mean meaning, you know, much higher or much lower than the mean. You know, appear much less frequently. Okay. And so we have a lot of things in nature kind of follow the normal distribution. Something exciting is happening out there. We are missing out. We have the exciting stats lecture going on the normal distribution. So
they don't even know what
yeah, they don't know what they're missing, right? All right, people, settle down out there. Okay. And so this is kind of what we have. So, you know, so examples of distributions that follow the normal distribution. So let's see. Maybe I'll have to go to the next slide here. Okay. You know, things that follow. Okay, so human height. General quote intelligence measures. So, and this is, you know, so things like IQ or, you know, SAT, you know, scores, you know, and whether they truly measure what, you know, whatever we construct as intelligence or whatever, you know, they're designed to follow normal distributions. You know, certain, a lot of things that appear in medicine, such as the example that the book has is serum cholesterol, so cholesterol levels in the general population. Okay, so there's a lot of stuff out there. So usually human height and really you know, any kind of things measured to kind of linked to bone lengths. Okay, so things related to your kind of skeletal structure will follow a normal distribution. Other aspects, you know, a little bit less so. Okay, and so you know, the neat thing about the normal distribution is that let me see if I could pull up the oh, maybe I don't have it. Okay. All right, I'm gonna give me a second. Okay, so we'll so anyway, this is what the normal distribution looks like. So whether the normal distribution looks like this or and we can scale it, you know, you can kind of stretch it out this way, whoops, and like squish them, so you can have kind of like normal distributions that are kind of spread out like this. You can have normal distributions that are really skinny also, but these are still normal examples of normal distributions, okay? So these are all examples. Okay, and then you know, you can stretch them and whatever, okay? Stretch them out. And the thing is that we can shade, if we shade all of the, so if we just imagine kind of these tails going off and kind of lining up, if we shade the entire area under the normal distribution, the amount we would shade would be equal to 1 or 100%, okay? So the total area under the curve would be 100%. And if I draw a line right here, and I shade just what's to the left, then the area shaded would be like 50%, right? Ooh, that is not what I want to do. Just kind of seal these off somehow. Is this going to work? Okay, no, it's not going to work. All right. They updated this software and like I don't know how to color things in anymore. Okay, so I'll just use a pencil here. Okay, so if I shade over here, the amount I have shaded will be what, 50%, right? And if I 50% shaded, 0.5. Okay, and then you know, you can imagine if I draw the same thing anywhere else, I would also have 50% shaded, okay? And we have our reference table, and what this tells us is it will tell us how much we have shaded if we kind of mark off places on the normal distribution here. So let me just kind of I'll just blow this one up. This is kind of our prime example here. Okay. And you can kind of we'll create little tick marks along the line. There's so if you draw your hill, okay, approximately where the I don't know, the inflection point is, so where it kind of there's kind of like a point where down the slope where it becomes like almost like a flat line. So there's always a little bit of curvature, and then around here it becomes flat. Around there is where you draw kind of your first tick mark, and then the distance between kind of this center to you know, right here is one spacing, and then we'll you'll have 2 and then 3 and then so on and so forth. Okay, and then you can just kind of imagine the hill going off like this. Okay, don't worry, I'm not going to judge how well you draw your your hills and whatnot. Okay, but the idea here is at the center we are going to put the mean, and we're going to put in the value 0. Okay, and here will be 1. And what this measures is, this says this is 1 standard deviation from the mean. Okay, so this location, this is 1 standard deviation above the mean. So I'm going to say a sigma here. Okay, so we are marking off our number line in terms of standard deviations. Okay. So this will be 1 standard deviation away from the mean. This location, this is 2 standard deviations away from the mean. Okay, and this here would be 3 standard deviations. So each time we're going out 1 sigma. So each, you know, a standard deviation is sigma. Okay, and so essentially this number line shows us how far we are from the mean in terms of standard deviations. Okay, so the axis kind of says, you know, how far are you from the mean? Deviations. Okay, and then so you know, over in the other way, we're, you know, 1 standard deviation below, 2 standard deviations below, 3 standard deviations below, etc., etc., etc. Okay. All right. Is everybody okay with this diagramming out? Okay. And what we say, you know, I don't know what's going on here. Maybe I'll try to draw this a little bit better here. I'm going to trace the normal distribution. Okay, sorry. Let me see if I can shape. I'm going to try coloring this in again. All right, so, okay, great. So if we go 1 standard deviation above and 1 standard deviation below, the amount shaded in this green region, okay, so the green shaded area is about 68%, okay? So about 2/3, a little over 2/3. Okay, and so basically what we're saying is that we expect about 68% of data to be within 1 standard deviation of the mean. So, if I have the mean right here at 0 and I go up 1 standard deviation and I go down 1 standard deviation, the total shaded area there is about 68%. So this represents about 2/3 of the total area in the normal distribution. Okay. And then if I were to just shade a little bit, shade a little more here. Okay. I don't know. Maybe that's. I'll pick a different color here. Okay. So now the green plus the orange represents about 95%. Okay, so green plus orange is about 95%. So we expect about 95% to be within 2 standard deviations of the mean. Okay. All right. And then if I go out to the 3rd standard deviation, okay, this encompasses almost everyone. Okay, we only have just a tiny little portion outside of this zone. Okay, so this is 99.7%. Okay, so green plus orange plus red is 99.7%, so almost all. Okay, so about 99.7% of the data will be within 3 standard deviations of the mean. But that also means just a small portion is still beyond 3 standard deviations from the mean. Okay, but this is kind of the theoretical shape of the normal distribution, and this is what we have. Okay, and so if I flip back a slide, okay, and if I were to kind of take this thing and draw little 1, 2, 3, go to these, this one which is way skinnier, we would have the same proportions, okay? 68, 95, 99.7. Okay, so if I were to shade these in, it would whoops, have the same proportions here. So even if I've stretched them out in terms of the proportions being represented, we have the same 68, 95, 99.7, okay? Even though it's way stretched out here. Okay. So this would be, 68% from here to here would be 95%, and then from here all the way to here would be 99.7%. Okay, so even though you you stretch out or you compress your normal distribution, you're still going to have the same proportions in between these things, as long as you're measuring in terms of standard deviations. Okay, so as long as you mark off your number line in terms of standard deviations, it will all have these things. Okay. Okay, and so we can use the reference table to kind of tell us how much is shaded. Okay, because for anything, so these are the 68, 95, 99, 7. Those are 3 numbers that you should try to memorize. Okay, so 68, 95, 99, 7. Okay, also known as the empirical rule. Okay. But these are three numbers to memorize for within 1 standard deviation, 2 standard deviations, and 3 standard deviations of the mean. Okay. But for everything else, we have the normal table. Okay. And so the way the normal table works is, you know, just imagine your number line again, 0, 1, 2, 3, marked off in terms of standard deviations from the mean. Okay. And you say, okay, well, if I were to draw a line at 0 and I shade everything to the left, how much will I have shaded to the left? 50%, right? So if I draw a vertical line at 0 and shade everything to the left, the amount shaded would be 50%. Okay, or I'll just say 0.5. Okay. All right, so now do a little bit of thinking here. If I draw a vertical line at 1 and I shade everything to the left, how much would be shaded? So I'll shade in a little bit of blue here. So 84%. Oops. Okay. Hang on. Let me finish drawing in this thing here. Okay. So then, yeah. So if I shade in this thing, so this would be kind of the. Okay. So this would be the blue area. Okay. And then if I draw, so I draw a line at 1. And shade everything to the left. Okay, so this will be the blue plus green area. Okay, shaded area would be about 84%. Are we in agreement here? Yes? Okay. Anybody having trouble seeing with the 84%? Okay, and we're getting that because well, we're saying, okay, 68% is between here and here. Okay, so if 68% is between here and here, then that means, well, half of that, so this part has to be 34%, right? Okay, and then so if we've established the blue was 50, so 50 plus 34 would make 84. Okay. Or the other way we could say is, well, if 68% is within 1 standard deviation, then, you know, how much has to be over here and how much has to be over here? We would say, well, total of 32 has to be out there, so we would have 16% out there and 16% out there. Okay? Is that all right? Okay. And so, you know, here's a question. What if I drew a vertical line not at 1, but I drew a vertical line at 0.5? And I shaded everything to the left. So let's actually we'll go over here, and so here I'm going to draw a vertical line at, say, 0.5, and I shade everything to the left. How much will I have shaded? Okay. Okay. So this is, you know, this one's a little bit harder, and this is where we need to use our table. Okay. And so we do know. Whatever our answer is, and this is where you should you can just use your brain a little bit. We do know that whatever answer we have has to be less than 84%, but has to be more than 50%, right? So if if we're using the table and we get some number that's less than 50% or more than 84%, we know we did something wrong. Okay. So, you know, if I wanted to shade this area in, and let's see if I can do this without coloring the whole screen. Okay, so whatever color this is, brick red. So apparently it's a known fact that in general women can distinguish colors much better than men. This is like if you just show a spectrum of colors, women have the ability to differentiate colors much better than men do in general. Of course, everyone's different, but I was like, oh, well, that's interesting. Okay, so your table. Let me pull up my reference table on. Where did it go? Okay. Okay, so when you look at your reference tables, it should look something like this, and if we look up this number 0 in the first column, 0.0, and I'm sorry, in the first row, 0.0, and the column 0.00, we see the number there is 0.5. Okay, and this means that if you look up the value 0.00, the area shaded to the left is 0.5, okay, or 0.5000. Okay, so it gives you 3 decimals of precision. Okay, so the table. So from the table, you know, if we look up 0.0 in the column 0.00, we have 0.5000, and this means the area shaded to the left of 0 is 500. Okay, and then if we went to the row 1.0 and the column 0.00, the area shaded to the left is 0.8413, okay, which matches our estimate where we said 84%. Okay. Now what we want to look up is the value 0.5. Okay, and so we would go to our table and we would say the row is 0.5, column there is 00, and so we have 0.6915. Okay, so this, whatever color this is, the shaded area here is equal to 0.6915. Okay. Now, if I were to move just a tiny sliver, okay, just a tiny bit, a little bit extra to the right, and I shaded this area in, okay, and so I wanted to add a little piece right here, okay. Now, how much will I have shaded total now? Okay, so let's say I am now located that this spot is now going to be 0.54, okay? And so in order to save space, the way our reference tables handles this is that it puts the value 0.54 in the row for 0.5, but you have to look up the value in the column where it says 0.04, okay? So rather than having to have one row for every single entry, it's going to say, okay, go to the row 0.5, but look in the column 04. Okay, and so it says, okay, well, the area now is going to be 0.7054. Okay. Okay, so the total area, so this will be kind of the, I don't know, the red, and this will be the red plus pink. Red plus, I don't know, rose pink color. And this is not even red, it's like, see on my screen it's more like a salmon-ish thing, but whatever, okay. You know, this doesn't have perfect color reproduction, this projector, so whatever, okay. That's alright. I'm not teaching Photoshop, so. Okay, and so this is what we have, so we see, okay, well, moving over just added just a tiny little extra area here, okay. We can also just ask, how much is unshaded, okay? So how much is still unshaded? Okay. Well, we know that the total area has to add up to 1, okay? So we can say, well, if the shaded area, total shaded area, including both the red and pink, is 0.7054, okay, and then the total area under the curve is 1, then the unshaded area must be 1 minus 0.7054. Okay, and so that is 1 minus 0.7054 is 0.14, or 0.2946. Is that good? Okay. All right, and so this, so everything I've been saying, all of this gives definition to the Z-score. Okay, so our normal table, you'll notice that in the top corner of your normal table, you have the little Z. Okay, and that's because it's often called the Z-table, or we're referring to Z-scores. Okay, and a Z-score is basically the distance a point is from the mean expressed in standard deviations. Okay, so I think we can do this, but let's say the average height of women, of adult women in the US is 64 inches. Okay, and we will say the standard deviation of these heights is 3 inches. Okay. All right. So I think this is very simple, but we'll just try this out and see. Say, okay. So I'll ask, what is the Z-score of a woman who is 67 inches tall? Okay. So 67 would be 5'7". 64 is 5'4". And then we'll just continue this on, and we'll say who is 66 inches tall. Okay. All right. So I'll give you like 30 seconds to figure the answers out to these questions. Don't shout them out. Don't shout them out. Just write them down, and then and we'll just go over these. Right. So I'm just asking for the Z-score. So what is the distance? How far is this? What is the distance from the mean expressed in standard deviations? Yeah. Yes.
Do you want the answer?
Okay. Yeah. Well, I mean, so does everyone? Did everyone get a chance to kind of write down these answers? Right. My hope is that this isn't too crazy hard here. Okay. But okay. So this one is just what? 1, right? So this woman has a Z-score of 1 because she is 3 inches above the mean, and each standard deviation is 3 inches. So she is exactly 1 standard deviation above the mean. So her Z-score is 1. So we would say Z is equal to 1. Okay? And this woman, her Z-score is not 0.33, but 0.667 or something around there. Like her Z-score would be 2/3, right? Because she is 2 inches above the mean, or 2/3 of a standard deviation above the mean. Okay? Is that good with everybody? Okay. So, I mean, if you had to come up with a formula for the Z-score, what would you say? we would say z is equal to, let's say we're going to take some point y, and we want to know how far it is from the mean, right? So what would I do there? Yeah, okay, I would subtract off the mean, okay, but I don't want just the distance. I don't want the answer to be 3 inches above the mean or 2 inches above the mean. So what do I have to do to this result? Yeah, I would then divide by the standard deviation. Okay, and so this is how we get our z-score. It's exactly what it is. It's the distance from the mean, okay, but not the raw distance. It's the distance from the mean in standard deviations. Okay, so the numerator would be the distance from the mean. Dividing by sigma turns that distance into how many standard deviations it is. Okay. Okay, and then by dividing by sigma, we get the distance in standard deviations. Okay, is that all right with everybody? Okay, and then so we can also just kind of flip the questions around, and so we'll say again, if I want to say adult women in the United States have heights that follow the normal distribution, with mean equal to 64 and standard deviation equal to 3, there's a shorthand way I can say this, okay? I can say y, so we'll say y will be heights of adult women, if you want to say okay, and we'll just say y, and then there's a tilde or squiggle that means comes from, and then we'll say capital N for normal distribution, and we say 64, comma 3. So this is a shorthand way of saying follows a normal distribution with a mean of 64 and standard deviation of 3. Okay, so just shorthand. And you often see this written in textbooks and things, whatever we have. Okay, and so so likewise, I could say, you know, how tall is a woman if her z-score is -2? Okay, and all right, huh? Yeah. So what's our answer would be 58 inches, right? Okay, and there's a couple ways you could have done this. One is you could have said, oh well, if her mean height, if the mean is 64 and this person is 2 standard deviations below the mean, we can say -2 times 3, and then you get 64 minus 6, and you get 58. Okay, so that's perfectly. I think that's what I did in my head. But and then another way is you could say, well, okay, well I know z is y minus mu over sigma. Okay, and so you can say, I can say, well, z is -2. I'm looking for y. I'm going to subtract off the mean of 64, and my standard deviation is 3. Okay, and then you would solve for y. Okay, solve for y, and then you say get -2 times 3 is equal to y minus 64, and then it turns out that the math is exactly the same, right? You add 64 to both sides, and you have 64 minus 2 times 3, which is exactly what we have here, and so you get y is equal to 58. Okay, so I mean, it's just the exact same thing. So, but that's what we have. Okay, so you can just plug it into the formula here and solve for your unknown, or just conceptually you might say, well, if I'm 2 standard deviations below the mean, this is kind of what I'm setting up here. Okay. Okay, so this is plug it into the formula. So this is kind of like just conceptual, and then this is also just kind of use the formula. Either way, do what's most comfortable for you. Okay. All right, and so so with this, we can now start to answer questions related to the normal distribution. Okay, so we can say things like, again, we'll say heights of adult women in the U.S. come from normal distribution 64, 3. Okay, and we could say, what percent of, I'm just gonna write women here, but when I say women, I mean U.S. adult women. Okay, and I don't mean to be like pedantic or anything here, but it is important because around the world, the heights and things are very different. And this is 64 and 3. This is just very approximate. It's probably the table gives you like 4 decimals of precision, but our answers will just be kind of ballpark answers. So I could say, what percentage of women are shorter than, we'll say, 5'5". Okay, so this will be 65 inches. Okay, so what percentage of women are shorter than 65 inches? Okay, and then so I'll give you a minute to figure that one out, and then I'll also ask, what percentage of women are taller than 5'9"? So that would be 69 inches. Okay, so so for here you would your steps would be find the z-score. Okay. And then step 2 would be look up the z-score and find the appropriate area, either the area to the left or the area to the right. Okay, so I'll pause the video here, and I think I'll do this one on the next page actually. Okay, so what percentage of women are shorter than 5'5", and then what percentage of women are taller than 5'9"? All right, let's see. Okay, so to solve this one, we're going to turn 65 inches. We're going to get the z-score for 65 inches, right? So our z for that is going to be 65 minus 64 divided by 3, and we get a z-score of 1/3, which in decimal form is going to be 0.3333, so on and so forth, okay? In order to look this up in our table, we're just going to round off to 2 decimal places. Okay, so we'll look up z equal to 0.33. Okay, and so this means we go into the row 0.3, and then the column 0.03. Okay, so in our table, I go to the row 0.3 and the column 0.03, and I get 0.6293. Okay, so from the table says 0.6293. Okay, so the table always gives us the area to the left. So essentially, you know, I've got 64 right here, I've got 65 right here, and I'm shading everything to the left. This is terrible. Okay. And so the table always gives us the area to the left, and that is the area that I want. Okay, so this is the area to the left of z equal to 0.33, and that is our desired area because it says shorter, right? So we do want the area to the left, so our answer is 0.6293. Okay, so what percentage of women are shorter than 5'5"? We would say 62.93%. Okay, 63%, that's probably good enough. All right, and then for the other one, I said what percentage of women are taller than 5'9"? So we followed the same process. We'd find our z-score for 69 inches. We subtract off our mean of 64 and divide by 3, and we get z is equal to 5/3, or 1.6666, so on and so forth. So when I look this up in the table, I'm going to just round off to 1.67. If you chose 1.66, I guess that's okay. But it probably should be z equal to 1.67. So again, this means we go to the row 1.6 and then the column 0.07. Okay. All right, and then what the table says, the area to the left, so from the table, the area to the left of 1.67 is going to be 0.9525. Okay. Now we want the what percentage of women are taller than 5'9", okay? And so we don't want the area to the left, we want the area to the right, okay? So the question asks for a percentage that is taller. So we want the area to the right. So we get 1 minus 0.9525, and we get 0.0475. Okay, so what percentage of women are taller than 5'9"? We would say 4.75%, or something around 5%, something like that. Okay. All right, is this good with everybody? Okay. So a neat thing about the normal distribution is that it is symmetric. Okay. So because the table is symmetric, okay, there are a few shortcuts you can do, or really just one shortcut. And maybe this is useful to you, maybe you don't like this, okay? And it will be that the area to the right of anything is actually equal to the area to the left of the negative z, okay? So the area to the right of z is equal to the area to the left of negative z, okay? Because it's symmetric, right? So you've got, if we want the area to, so I don't know what your picture looks like. Okay, so if you want the area on this side, okay, so if we want the area to the right over here, okay, I can look up this thing and find the area to the left and subtract, subtract that from 1, okay? Or because it's symmetric, I can look up the flip of that and get the just the area to this way, all right? So we can do that, and we can see that when we wanted the area to the right of 1.67, okay, so 0.0475 this is the area to the right of z equal to 1.67, okay? Now, if you look up negative 1.67, you would see we would get 0.0475, okay? So, you know, if you looked up negative 1.67, okay, we get 0.0475 there. Negative 1.67, we see that, okay? And so, so that's just like a nice little thing that you want, that could be helpful, okay? So the area to the right of z is always going to be equal to the area to the left of negative z. So if you can imagine something like this, and we want, you know, what's over here, we can just kind of, if this is z over here, we can kind of flip this around and just find the area to the left of negative z. Okay, so it's a little bit of a shortcut because the table will always give you the area to the left. Okay, so you know, if you're not comfortable doing that, don't worry about it. Okay, but it's a nice little shortcut that exists. So you can always find the area to the left and subtract that from 1, and that will give you the same answer as well. Okay, why don't we take a short break here? We'll say 10 minutes, and then we'll finish out chapter 4. Talk a little bit about some other stuff.